Is Bill good? Okay, welcome back. We covered a lot yesterday. Today we're going to cover a lot. Is everything okay? Okay. Today we're going to cover a lot on more memory technology. But before we start the lectures, let me very quickly go over DRAM versus SRAM. I'm not going to spend a lot of time over here. This is very basic. But we've been discussing DRAM. In DRAM, capacitor stores the value in terms of charge. And this is really the charge storage unit. And this is why DRAM has been quite successful, because it's very dense, as you can see. And then you have an access transistor. And we talked about refresh, and we're going to talk a lot more about that. Giray will talk about that. Giray will also talk about accessing a DRAM cell and how to reduce that access latency. And we've covered some of this, so that I'm going to go through some of these slides very quickly and then turn over to some of my students who will deliver some of the lectures. But this is just to remind you what's happening. You have the capacitor access transistor. This is 1 bit, and you enable the word line. And once you enable the word line, you share charge with the bit line. So this is the structure of a single DRAM cell connected to a bit line and a sense amplifier. Okay. You enable the word line, charge sharing happens. The little charge in the capacitor perturbs the bit line, and that perturbation gets sensed by the sense amplifier. There needs to be sense amplifier enabling also. So there's some things that goes on, but this is the basic operation. I think we've discussed that yesterday also. Static random access memory essentially is another technology. This is one way of implementing it. Essentially, you have a cross-coupled inverter that traps the charge, and you've seen this probably in your digital design lectures. You have 4 transistors for storage, in this case 2 transistors for access, but in modern technologies it could be 8 transistors also. And in this case you do differential sensing with bitline and bitline bar. And as I mentioned yesterday, all memory technologies look alike. Internally they consist of these 2-dimensional storage arrays. This is a bank we've covered yesterday, so I'm not going to go through this in detail. Giray will talk about some of these when he talks about latency, right? Okay, again, I will not go over some of these details, but the reason I'm actually going through these slides is to talk about trade-offs. It's really important. This is the reason for the memory hierarchy, basically. There's no memory technology that's good at everything. And these are some of the trade-offs associated with DRAM and SRAM. And green is good. Red is bad in this particular case. Clearly, DRAM is slower access, SRAM is faster access, and part of the reason is the capacitor, existence of the capacitor in one versus not in the other. And DRAM is much higher density, lower cost as a result. And we'll talk about refresh. We'll talk about retention time. We talked about this briefly yesterday, but I will talk about more. And refresh overheads are increasing, and we'll talk about how to alleviate them. Okay, but this is the major reason I wanted to actually talk a little bit more over here. We should not ignore emerging memory technologies, even though we're not going to cover them a lot in this course. I think we should be always forward-looking. At some point, I believe it's going to be very, very hard to scale DRAM and SRAM. And at some point in the future, we'll transition to some other memory technologies. Even though it may look very far at this point, I believe this will happen at some point. That's true for logic also at some point, right? So I mentioned, we talked about phase change memory yesterday briefly, but this is one example. Again, I'm not taking any sides in it with any technology because some people are actually developing these technologies and they have vested interest. I don't have any vested interest in any of these technologies. I just believe that research should be done to enable some of these that make sense, right? So I'll just give you one example. In this case, phase change memory. You have phase change material that exists in 2 states in nature, amorphous state and crystalline state. And these have completely different properties. And there's a very wide range in terms of these different properties. For example, in amorphous state, this material has low optical reflexivity. In the crystalline state, it has high optical reflexivity. This means that if you actually shine light on this, you can detect whether you're in the amorphous state or crystalline state. And that's one reading mechanism. And I would like you guys to think about, there's no single reading mechanism of a memory. It's really how you design it. And this is done, actually. This is in rewritable CDs, you do optical reading of the same type of memory or similar kind of material, let's say. But this is a very slow process, actually. Optical reading of this sort of material is a slow process. It's also, the amorphous state is also high, has very high electrical resistance, and crystalline state has very low electrical resistance, and the resistance range is very large. Meaning you can actually detect the resistance of the material, and that's another reading mechanism. So the same material can be read in different ways. So the fundamental thing that I want to I want you to take away is you have a storage device. In this case, it's this chalcogenide glass. That's a storage device. That's independent on how you read it. Reading mechanism can be very different from how data is stored, right? You can read it optically, you can read it electrically, you can read it by detecting the voltage, you can read it by detecting the current or detecting something else, right? And the reason why this became very interesting beyond rewritable CDs is because at the very low level, companies like IBM and Samsung have developed mechanisms to read it very fast by detecting the electrical currents. Again, I will not go into the detail. As I mentioned last time, I don't think it's in these slides, but the IBM paper in Journal of Research and Development in 2008 has a great overview of the technology and the reading mechanisms of this technology. So we were actually quite excited about it at the time. Some of these changes were happening in industry, that you could read this material very quickly. And we did some work along with others in the field also. These were some concurrent works that happened initially in 2009 or so. I'm going to reference some of these papers. And we basically kind of envisioned the future where DRAM, which has a lot of technology scaling problems, which we have discussed and we're going to discuss more, would be over time replaced by phase change memory. This is kind of the most aggressive feature, if you will. But I think the more realistic future is probably more hybrid feature, because as I said, I don't think phase change memory has properties that is going to completely make DRAM obsolete, if you will. But that's what this is what research should do, I think. Research should pose the aggressive question, can we actually replace this existing technology with some other technology that we don't completely know, but we can maybe architect over time, right? Okay, so that's what I wanted to mainly say, and this is the paper we wrote. There are other papers. If you're interested, you can take a look at it. We're not going to cover this stuff in these lectures more. Now, I should say that we were very happy to see that based on all of these efforts of the community, Intel announced this. How many people use this in their machines? Nobody. Well, I'm not surprised because it was expensive, but this is Intel's phase change memory. They call it 3DX point, and they manufactured it. You could have bought it until recently. I don't know. Maybe you can still buy it if you want to experiment with it. So this enables, I think, a lot of opportunities. So you could put this in your memory slot, and this could be part of your main memory. That's the good part. I will not talk about that in more detail, but I believe, as we discussed yesterday, it enables a lot of opportunities. Now, the problem is this is really a trade-off in the end. You can see that the trade-off becomes a little bit more complex over here. DRAM is actually lower density than phase change memory. You could actually make it a much higher density. Both of them have manufacturing issues compared to conventional logic process. And clearly, phase change memory manufacturing is much less mature because it's an emerging technology. DRAM has had 60 years of run for it. It was invented in 1965 by Bob Dennard. You can read the patent in 1967. And it has been, whenever you think of emerging technologies, always think of existing technologies have had 60 plus years of run to them. Emerging technology has started maybe in 2000 or so, right? It's not exactly 2000, but it's around that, let's say. So it's not a fair comparison to say, oh, this emerging technology is not good. Maybe it has not matured yet, right? So we did scaling studies saying that this will scale much better into the future, for example. And as we said, one of DRAM's advantages is no endurance problems. Whenever you write data, you don't actually destroy the cells. You don't actually reduce your capability to read or write data in the future. Now, this may be changed in the future. There's no wear out in DRAM as far as we know, but there may be some things with very smaller technology nodes. We'll see about that. But phase change memory clearly has endurance problems. Whenever you actually write into a cell, it really degrades the contacts. The reason is you actually apply very high temperatures and high currents, and as a result, you really degrade the contacts. And over time, if you keep doing this right, you degrade it more and more, and at some point, you cannot write to or read from the cell. Now, this is a problem, clearly, and flash memory has a similar problem with different underlying physical mechanisms. But if your main memory is exposed to this sort of endurance problems, then you need to manage that main memory in some way, right? And again, I'll leave you with that. I'm not going to talk about the management mechanisms. But you can see that there are interesting trade-offs over here. DRAM has much lower access energy, for example. PCM has higher access energy. DRAM is faster. PCM is slower in terms of access. And the order of magnitude, well, factor is about 4x. So PCM is about 4x slower. Which means that if you replace DRAM main memory with phase change memory, you immediately get a 4x latency hit. That's very hard to overcome, unfortunately. That's why you need some hybrid memory. Now, GI is going to talk about latency reduction even in DRAM. Even DRAM latency is not improving, as we discussed yesterday. It's not going to improve that much, but there are ideas to improve it in better ways. Okay, so hopefully this gives you an idea. So basically today, it's not just phase change memory. There are other resistive memory technologies. Resistive memory technology, essentially, resistive memory technology means that data is stored in terms of resistance value, right? For example, a resistance value, basically different resistance values determine the different data values that you have. And if you have a resistance range, you can chop it out into intervals, and different intervals may encode different set of bits. For example, you have a multi-level cell. You can actually chop up your resistance range to 4 intervals, and you can encode 2 bits that way, right? This is very hard to do in DRAM. You could do it in flash by actually chopping up the voltage range into intervals. But DRAM and flash are charge-based memories, and they're quite successful. Emerging memories are usually resistive type of memories, and we'll see if they succeed. People are trying, and as we discussed yesterday, there are actually small examples of edge devices that may have MRAM, for example, but we'll see if they can be successful in the larger scale. And it's good to push towards that for sure. Okay, so just to give you an idea of some of these other technologies, I think we've already discussed phase change memory, but in STT-MRAM type of technology, what you have is a magnetic memory, essentially. You have some magnets, and essentially the polarity of the magnet determines whether or not you store a 1 or 0, let's say. And you can inject current to change the polarity of the magnet. Essentially, the polarity of the magnet is measured compared to a reference magnet, and if that polarity is the same direction or different direction, that encodes the data. That's what I mean by, and the reason it encodes the data is because resistance is determined by whether or not you're in the same direction as the reference magnet versus the other direction in the reference magnet. And again, you can do multi-level cell over here because your resistance levels can be different inside that resistance range. But this is a very different way of reading and writing again, right? As you can see. On the other hand, memristors, RRAM, ReRAM, I kind of group them over here together. And there are other technologies that I kind of omit over here. But you usually inject current to change some sort of atomic structure, and resistance is determined by the atom distance. Right? Okay, again, I will not go through this in a lot of detail, but we have a lot of lectures on this topic that I will refer you to. And actually, this is interesting because if you have this sort of resistive memory technology, I'll actually use this slide to cover something. Normally what happens today is, as we discussed yesterday, right? You have disks, right? In your disks, normally when you want to access files in your disk, you need to go through operating system structures to do the translation, and you map the file to main memory, and then you modify the file inside main memory, and then you write the file data back into persistent storage. That's a lot of overhead. And people have actually realized this overhead many, many years ago also. There are beautiful works by IBM. I actually recommend a book by Frank Soltis. This is an IBM engineer. These guys worked on single level stores. And the idea is essentially, instead of accessing memory and storage in different ways, why don't we just use load and store to access everything? Right? That's the idea. With these emerging technologies, that becomes more possible. Right? Okay. So basically, what happens is if you actually have a very slow device over here, which is a hard disk or an SSD, the software that you use to access it can be slow because the device is very slow to begin with. If you actually make it a little bit slower, it doesn't matter. But if your device over here to access that stores your files or persistent data is very fast, almost as fast as DRAM, then the software that you use to manipulate files becomes very, very expensive. You don't need to basically going through the file system to map the data back into DRAM starts making no sense. So if some of these disruptive memory technologies happen, and if they replace most of your storage or some of your storage with these very fast technology like phase change memory or STT-MRAM, then we really need to rethink the software layers as well, because we cannot keep the same storage model that we have. So we've argued that we should go to a one-level memory and storage model as well if you have these technologies. And with one-level model, you essentially have loads and stores with some metadata associated with them. And these loads and stores enable you to access either persistent data or volatile data. So DRAM and persistent memory can be a heterogeneous memory underneath. Okay, I'm just giving you some ideas over here without going into a lot of detail, but these emerging memory technologies can enable a lot of other things than we might have initially actually thought about. Okay. I should mention that, okay, I'm not going to go through that, but I should mention that I see a very dangerous path in research in general. So after Intel decided to discontinue Optane memory that I showed you earlier, and they did that a couple of years ago, I think, a lot of academics said, oh, we should not do research in this area. That's very bad. The fact that Intel discontinued an emerging memory technology doesn't mean that emerging memory technologies are fundamentally bad, right? Intel clearly has their own business reasons, which may have nothing to do with science or research. I should mention that because it's really important to set the stage this way. And I don't believe Intel discontinued it because of fundamentally bad properties of phase change memory. It may not be a good business decision for them, right? So those business decisions really should not affect academic research. But we see that a lot, I think, sometimes in academic research in DRAM as well. So if you're working on emerging memory technologies, keep working on it. Okay, so as I mentioned this yesterday also, but essentially, this is one of the reasons for working on it, right? Flash memory was a very doubtful emerging technology for at least 2 decades. And now flash memory is everywhere, and it's changed our lives. Okay, I'm going to skip a lot of these because I want to give time for my students to give the remaining lectures. Any questions on this before I hand it over to Giray? So Giray will talk about, oh, you had a question? No. Giray will talk about DRAM latency, retention time, and then we will talk about read disturbance issues, and then later we will switch to systolic arrays and genome analysis acceleration. Cool.
I've already shared the screen. Is it shared on Zoom? Okay, perfect. I think everything is good, right? Should I hide this? Okay. Hello, everyone. Welcome to this lecture. Thanks, Onur, for kind introduction. So we will talk about memory latency, data retention, refresh, and RowHammer now. And then in the afternoon as well, we will keep talking about RowHammer. It will not be me, but some people will. So this is me. I use the name in the middle, Giray. So I'm a researcher in a software research group since 2016, and I just defended my PhD thesis. And there are some links here. I do research in like whatever Safari is interested in, basically. So I'll just provide a quick recap about DRAM background. So when we look at how DRAM is organized, this is a picture of a DRAM module. We have a set of chips that form a DRAM rank, and within each chip, we have multiple banks that Onur already talked about. And within each bank, we have multiple subarrays that includes two-dimensional arrays of DRAM cells. So we access these DRAM cells internally in a DRAM row granularity by activating or asserting word lines. And when we do that, there are some vertical bit lines that connect these cells to a row buffer structure that where we can perform read and write operations. So this is another cartoonish picture of a DRAM subarray. Here, let's say we want to access the second row here. We first need to send a command called activate, which fetches the row's content into the row buffer. And then we serve the column accesses from this row buffer structure. And then once we are done with this row and we want to access data in another row, we first need to send a pre-charge command, which essentially disconnects the row from the row buffer and the bit lines, and also prepares the bit lines for the next activation. As Onur mentioned, DRAM is a volatile memory technology, so you fully charge it, but it leaks charge over time, and you can lose data. To avoid that, we need to periodically perform this DRAM refresh operation. It's a key maintenance operation to avoid such bit flips. And what it essentially does is it activates a row, fetches the content to row buffer, amplifies it, and then writes back, and then closes the row. And the problem is that when you refresh a DRAM row, it essentially blocks all other accesses to the whole bank or even rank. This is the promised updated plot from yesterday. So on the x-axis, we go from 1970 to 24 now. As you can see, the DRAM chip capacity increases a lot over generations. We see more than 1 million times of capacity improvement. But when we look at the different access latency parameters, you don't have to worry about the abbreviations over there. These are basically the latencies of the activation, pre-charge, and other operations that I mentioned a little bit earlier. When you look at that, it's only like a few orders of magnitude reduction, less than an order of magnitude reduction, actually. And when you look at the recent years, you can see actually that there's not much scaling going on, especially for latency. So, and we know that latency is important for our systems. So we want to understand and exploit the variations in DRAM latency. So it is possible through testing real DRAM chips, because we need to understand their characteristics, behavior, their limits for reliable operation. And this is an infrastructure that was built over years and finally published in 2017. And it's open source on GitHub now. It's very easy to use. It has a C++ API. You can just download it and connect it to a FPGA board, basically, and use it. It's quite flexible. It provides us fine-grained control over the DRAM commands that we send to the DRAM chip. We can play with the temperature, many other parameters as well. There's an updated version of this as well that will be mentioned later. But this is the full reference for SoftMC. Okay, so I'll talk about several papers. This is the first one, adaptive latency DRAM. The key idea is to optimize the DRAM timing parameters online. So it has two components. The first one is that DRAM, it's provided by DRAM manufacturer, ideally, a set of reliable DRAM timing parameters for different temperatures for each module. And your system monitors DRAM temperature and uses the appropriate timing parameters. So yeah, you have DRAM temperature and reliable DRAM timing parameters associated to that. If you just do this like minor improvement in your system, instead of using the same parameters for the whole operation, you can get quite some reduction in your latencies, actually. So this is the results from testing 115 different modules. overall, when you look at the read and write latencies, you see like significant reductions around like 32%, 55%. And for the individual operations like activation or column accesses or pre-charge or charge restoration, there's some significant reduction that you can see in this paper. So it's quite promising, actually. And it's tested on a real system with these parameters and on different workloads, of course. And here are some evaluation results for performance improvement. So here you see some single core workloads and how much performance this method can give you by reducing the access latencies to memory. So for non-intensive, it's a bit modest, 1.4%. For intensive one, 6.7%, which is better. And overall, it's like around 5%. This is only for single core performance. And when you go to multi-core evaluation, actually, the story changes a little bit more. You see much larger improvements in the multi-core systems because latency becomes more critical. Okay. So reducing latency also reduces energy. How it happens, you finish your operation earlier, so you consume less energy. So LDRAM reduces the DRAM power consumption by 5.8%, and it's mainly because of the reduction in raw activation time. When you look at the advantages and disadvantages of this LDRAM, it's a simple mechanism to reduce the latency. You just get a bunch of different parameters and measure temperature, just use them. It's very straightforward, and it has some significant system performance and energy benefits, and benefits are higher at lower temperature because you can reduce the latency more, and it's low cost, low complexity. You don't have to change many things in your hardware. But there's this disadvantage that will keep coming up. Keep coming up. That it requires some higher testing cost, right? So you need to test and verify your chips more intensely. Okay. So this is the full reference for this paper, and there are a lot of links, so you can just look at the individual slides for this paper as well. Okay, so we have different types of latency variation as shown in this paper. It actually exploits the latency. Sorry, go ahead.
Can you go back to the slide with the paradigm and the performance? In the baseline version, but the improved version, do you employ any detection mechanism? Like all these latencies completely exposed, or because I guess that the performance improvement would be diminished if you use any kind of capacitor, right?
I don't exactly remember actually what was the professor configuration for this paper.
This is on a real system that already has a lot of data.
Okay, so it's already included.
Yes, it's already included. It's on top of whatever AMD employs.
Okay, so
thanks for the correction. Okay, so in LDRAM, we look at the variation across time with different temperatures and across chips. But are there other variations in latency across different things? So what about within a chip, right? So there's a follow-up work actually that does that, that looks at the latency variation across rows, columns in a chip. But there's some preliminary data here as well. So when you look at so this is a heat map basically. On the x-axis, you see the cache line address, and on the y-axis, it's row address. And the dots show the bit flips over there. And you see that they're actually accumulated on some particular columns. Basically, you can also exploit that, right? So DRAM timing errors are concentrated in certain regions, and for that, we have another mechanism. This is another paper that's published in 2016 called Flexible Latency or FlyDRAM. It's a software transparent design that reduces latency, and the key idea is to divide memory into different regions so that your memory controller knows like which part has lower access latency, which part has higher access latency, and leverages this heterogeneity in a smart way. So if you look at so this is some experimental results. So in the baseline DDR3 configuration, you just use the same latency value for all parts of the memory, right? And if you look at the profile that is collected from real DRAM chips for 3 different DRAM chips, you can see that the latency for the baseline was 13 nanosecond, but you can actually access pretty much everywhere. For example, for D3, you can access pretty much anywhere with using the latency of 7.5 nanoseconds, right? And for different DIMMs, partially you use 10 nanoseconds, another part 7.5 nanoseconds. So you can use this heterogeneity to provide performance improvements. And the upper bound is 7.5 nanoseconds in this case. And when we look at the performance impact of this latency reduction, it actually provides even higher performance gains, around like 19.5% up to. So advantages again, it reduces latency significantly, it provides performance improvements, and it exploits the variations within the chip on top of what ALDRAM did for across temperatures and across DRAM chips. Again, it has the disadvantage of higher testing costs. So testing is quite important in this context. And it requires slightly more complicated controller because it requires conveying that information about like different parts of the memory having different latencies. It needs to map data accordingly. Okay, so here we take a step back basically and try to understand why there is this spatial latency variation in the chip. So it's another paper that looks into the design-induced variation inside DRAM chip. It's called DIVA DRAM. So basic observation is that if your row becomes farther away, from the sense amplifiers, your access becomes slower. Basically, you need to your signal needs to propagate through a longer line. And across column as well, as you get farther away the word line drivers, you get slower. So this is the basic, not basic, this is the main observation that this paper provides. And it tells you that if your data is closer to word line drivers and sense amplifiers, you can access it really fast. And some cells are inherently slow just because of the design. So the systematic variation is caused by the physical organization, basically. So this paper proposed online profiling, DIVA. It shows, it profiles only the slow regions to determine the minimum latency, and it provides a dynamic profile and low-cost latency optimization. There are also, on top of this design illustration, of course, there are also cells that are scattered around. Like in a fast region, there can be some slow cells that can be caused because of the imperfections in the manufacturing process and the variations caused by that. And we can call them like random errors, and we can also address them by using error correcting codes. And the design induced variations are more localized, and you can deal with them by doing online profiling. And this paper combines the error correcting codes with online profiling, and it reliably reduces DRAM latency. And here you see the results. So the first one is ALDRAM, the first paper that I talked about. The next one is 2 variations of DIVA. In the first one, we only reduce the latency by using DIVA's profiling methodology, and we already provide a larger reduction in the latency by doing that. And you can also use this in a smarter way. You basically shuffle your data in a way that you can leverage these fast cells better, and you can further improve the latency reduction. And yeah, these are the results for read, and the other ones are for write. So DIVA DRAM reduces latency more aggressively and uses ECC to correct random slow cells. Advantages: it automatically finds the lowest reliable operating latency at system runtime, and it reduces latency more than the prior methods, of course with using ECC, and it reduces latency at higher temperatures as well. Disadvantage, it requires knowledge of inherently slow regions, and it requires ECC. And this is the full reference for that. So far we only looked at the latency, and we also said that it has some impact on the power. But if you think about it, when you play with latency, you can actually play with the voltage as well, because they are quite related to each other. And what if you want to optimize your system for like energy efficiency? What can you do about that? So the next paper looks into that. The main motivation of this paper is that DRAM power, DRAM is a large power consumer in modern systems, and it's low voltage DRAM reduces voltage quite conservatively to save energy and power. And our goal here is to understand the heterogeneity and exploit the reliability and latency behavior of real DRAM chips under aggressively reducing voltage, reduced voltage operation. And our key observation is that you have a huge voltage margin in the safety margins, or as known as guard bands. Errors can occur in very low voltages, basically, compared to the nominal voltage specified in the datasheet. And errors exhibit some spatial locality, and higher operational latency can mitigate these reduced voltage-induced errors. And this paper proposes a mechanism called Voltron that dynamically changes this latency and voltage setting to provide a good energy reduction. In this paper, we use SoftMC as the test bed. So we test quite a few DRAM chips. I don't remember the exact number, it will come. Yeah, so we adjust supply voltage, DRAM modules. We change it by using this little voltage controller here. And then we also schedule DRAM commands precisely with like 2.5 nanosecond precision. So here in this plot, on the x-axis, we have the supply voltage that goes from, like, the rightmost one is 1.35 volt, it's the nominal voltage level, and we go from right to left while we reduce the voltage. And on the y-axis, we have the fraction of cache lines with errors. So in a sense, it's like bit error rate. Sorry. Okay. So as we reduce voltage for 3 different manufacturers, you see that different manufacturers start experiencing bit flips in different voltage levels. So there's a minimum voltage that until which we do not observe any bit flips, and then when we further reduce voltage, we start seeing a lot of errors appearing everywhere. So reducing voltage below Vmin causes an increasing number of errors. So to show how this happens, we also conducted some SPICE simulations using the circuit model, and I show that when you reduce voltage, actually your access latency increases for activation and pre-charge operations. So if you keep using the same activation and pre-charge timing parameters and reduce voltage, then you, of course, experience bit flips. But this suggests that if you increase the latency, then you can actually mitigate these bit flips. So reliable low voltage operation requires higher latency. So with higher access latency, we can reach fewer errors. So we measure minimum latency that does not cause errors in DRAM modules. And here's a bubble plot that shows the population of the DRAM rows. So 1.0 is like 100% of the rows do not experience any bit flips. They reliably work, basically. And if you look at like this 0.4, for example, it's like 40% of the modules can work at that point. Yeah, so this is basically showing the distribution of the latency in the total population. And this dashed line shows the lower bound of the latency because we measure it with a precision of 2.5 nanoseconds. The main takeaway is that DRAM requires longer latency to access data without errors at lower voltage. And we look at how these errors are distributed in our DRAM chips, and we show that in certain modules they're all concentrated on certain banks. So if you change voltage individually for different banks, then you can actually further improve the benefits of this method. So yeah, errors concentrate in certain regions. So with these observations, this paper proposes a mechanism called Voltron. So Voltron works in this way. Basically, user specifies a performance loss target, and then Voltron finds the minimum voltage that can operate within that performance loss target. So how do we predict the performance loss? We use linear regression for that. So this linear regression model gets the applications characteristics and different DRAM voltage settings and latency relation as the input, and then it predicts the performance loss based on whatever voltage you want to use, and then it chooses the minimum voltage that remains in that performance loss target. Okay. So here are some results. On the y-axis, you see the energy savings, and on the x-axis is the memory intensity for low and high workloads. And we show some significant improvements in energy savings, basically. Okay, so advantages, it can trade off between voltage and latency to improve the energy or performance, and it can exploit the high voltage margin present in DRAM chips. Again, disadvantage, it requires some rigorous testing, so it increases the testing cost. Okay, so this is pretty much the end of the latency part, but I just want to keep this question here. So we can sacrifice reliability of some, if we can sacrifice reliability of some data, can we further reduce latency? Can we make use of it? And I will not answer this question in this talk, but I guess later in some other talks during track 4, the EDM paper will be presented, so you can get more information about this route of line of research as well. So in summary, for low latency, our goal is to, not our goal, basically the design of this DRAM microarchitecture's goal is to maximize the capacity per area, so increasing density, but not minimizing latency. And the current approach is one-size-fits-all kind of approach, so you use the same latency parameters for different temperatures, chips, different parts of a chip, different supply voltage levels and application data. But you can actually see a strong heterogeneity across these. So it makes sense to actually leverage this heterogeneity. So we want fundamental low latency computer architectures. And our important takeaway from these works is that main memory needs intelligent controllers for achieving better performance, lower latency, better energy efficiency. And okay, so this is the end of the latency part, and I'm not sure how we're doing with time.
Are there questions?
Are there questions? Yes.
The first one is related to the EVA online profile.
Yes.
So you said that smaller the submatrix.
Yeah.
So it's when we are closer to the woodland driver sense amplifier, then we are going faster. So is there a maximum point for the minimum size of the submatrix?
I couldn't get the last part. What is the question?
The closer we get to the
yes.
driver, sense amplifier, it gets faster. So obviously, smaller submatrices will be faster.
Yes.
Right? Is there an optimum point for going smaller in the submatrix?
If you're optimizing for latency, I guess you would just like put a row and then subarray. So, sorry, like a subarray contains only like one cell, right? In that case, you have the best latency. But yes. So you have a lot of overhead in your I/O circuitry over there. You need to repeat your row buffers and decoders quite a lot of times. So when you optimize for density, then your subarray size increases a lot. So there's a lot of cells in it, and then you have that variation. The trade-off is more like about latency versus density.
And there's a
It's more like a business decision, I guess. Do you have any?
If you want to minimize latency, as you said, I think you want one cell, right? Or one row of cells. I mean, the problem is he didn't cover one of the works that tackled this issue. Actually, it's called tiered latency DRAM. Was published in HPCA 2013. If you're interested, take a look at that for sure. But essentially, you have the trade-off that as your array size becomes larger, your interconnects become longer, and that increases your latency. The real overhead is really as Guy mentioned, the peripheral circuit, like the row decoder, and also the sense amplifiers. So just to put things in context, sense amplifiers are 1 or 2 orders of magnitude larger than the cells. So if you reduce the array size, you add more sense amplifiers and more row decoders, and that loss is huge, and that eats into your capacity. So right now, manufacturers determine the array sizes such that they get quite good capacity without, let's say, unreasonable latency, while also having good enough reliability, let's say, because as your interconnects get longer, reliability becomes an issue as well. It's a tough space to make decisions.
I have a question about the latency versus focus.
Yes.
So when you go lower, and lower energy, right?
Yeah.
But there is also a drawback that the capacity is such capacity because of the energy, right?
Mm-hmm.
So you would be refreshing more.
That's true. Yes.
And you use more energy to build possible more.
Yes, that's true. So, but the reduction in that voltage scaling part of that paper is not really. Maybe I should repeat the question. So when you reduce voltage, you can compensate or mitigate those bit flips by increasing latency. But there's also less charge in your capacitor, so your data retention time will be smaller, and you need to refresh more frequently. That's true in high level. So in that test, the scaling doesn't go to really like very low levels to require like more frequent DRAM refreshes. The paper actually looks at that as well. But I will cover more DRAM refresh related stuff here. So there are also some guard bands over there. I will talk about them. Is it satisfying? Okay. Any other questions? Okay.
Questions? Maybe I will say a few more things. I think Girai covered like how to exploit the variation in latency in existing chips, but you can also re-architect DRAM. That was the first point. Can you go back to that slide?
Which one?
The previous one. Yeah, this one. Basically, he didn't cover the reason 1. So how do you tackle? He covered the reason 2. How do you tackle that? And we'll cover that more. I mentioned the Eden paper yesterday, right? If you could, for example, reduce the latency for those parts of your application that can tolerate errors, you can actually get much better performance and energy efficiency. And Eden paper shows that. We'll cover that later on, hopefully. But the first part is also very interesting today, I think, because once you start rethinking your memory as a computation substrate, you want to also reduce the latency. You have computing inside the memory, right, or near memory. If your latencies are large, you still need a lot of caching and hierarchy in the device, in the computing substrate over there. But I think it's really important to reduce latency inside the device fundamentally so that your computing is also very efficient. So we didn't cover reason 1 because we don't have a lot of time, but there are works in that direction also. I mentioned the tiered latency DRAM work. The idea over there is to, as opposed to having bit lines that are long, segment the bit lines. Meaning divide the bit lines into 2 portions, isolate one from the other, and part of the array can be used as a fast cache. And this is one of the initial works. There are also later works that improve upon this idea. But I would recommend people to think about that direction as well. Basically, today's DRAM is not designed for low latency, nor is it designed for computing inside memory. So when you're doing computation near or inside DRAM, you're working against both of these currents. So it's good to think about that. Yes.
Kind of related to this property validation. So you mentioned that we have DRAM and 6 years should be really, really mature. I understand why we have that variability, or is it because
scaling, so whatever scaling is not also an issue.
Like this sort of variability? Yeah. I mean, it's manufacturing variation in the end, right? If you look at, I mean, you didn't show those pictures where some cells are strong. You had those pictures, I don't remember, but so in the end, you have huge variation across different cells. Some cells are really strong, some cells are really weak. Now, in this case, what does a weak cell mean? Weak cell is a cell that you need to access longer to access correctly. And that variation exists within the device, and it's a huge variation. And that variation also exists across devices. So some devices, the weakest cell is stronger than some other devices. And this is pure process manufacturing variation that is very hard to control in the end. And yes, as you mentioned, as technology scaling continues, this variation increases. And that's what we see in our results also. Does that make sense? Yeah. No.
Does it simplify or improve a lot, like performance?
I mean, embedded DRAM is much less dense. It's compatible with logic. So you won't get the same density. So people try to use this less level caches. In the end, the same issues exist over there also. I mean, we have not characterized embedded DRAM since we don't have access to embedded DRAM, but the same sort of variation exists over there. But the issues in embedded DRAM are less because you can integrate into logic. So it's meant to be a technology that's integrated together with the CPU chip. Okay. So in the end, even though we showcase DRAM because we are able to test it, I believe all of these apply to other technologies as well. In fact, we have papers on phase change memory, for example, where we try to reduce its latency by exploiting partition level parallelism. Another question for Girai, maybe.
Yeah.
You mentioned that the error shows some kind of special value. Do you have any insight why or how?
We can speculate about that, yes. So power distribution can be one thing. Another thing can be like because of some design decisions, some banks are less reliable, or I don't know, you can think about like how these banks are located in the wafer, right? Maybe like some parts of the wafer are less reliable. I guess like there can be many ways of speculating about that. We don't have really like a concrete data that shows the root cause. Exactly. Yeah. Any other questions? Okay, I'll go with DRAM refresh then. So this is just a reminder about this early memory scaling paper. As we scale memory, we expect some reliability issues. And this is, again, early work that projects that capacitor, as we go forward and reduce or increase DRAM density, reduce DRAM cell size, it will become more challenging because capacitors must be large enough to for reliable sensing, and access transistors should be large enough for low leakage and high retention time. And scaling beyond some technology nodes will be quite challenging. This is some data that shows that as you increase density, you have more failures in your server systems that Onur covered yesterday. You can find more details in this paper about this. And with this quick recap, I'll continue with DRAM refresh. So DRAM capacitor charge leaks over time. And the memory controller needs to refresh each row periodically to restore this charge. So basically, we need to activate each row every n millisecond. This n number was 64 milliseconds until DDR4, and now it's like 32 milliseconds for the normal operating temperatures. In high temperatures, you need to even go down to 16 milliseconds. And downsides of refresh, first one is energy consumption. So if you remember how you refresh a row, you basically activate it and then pre-charge. and it's really drains a lot of energy. So it's an energy hungry process. Also, it causes performance degradation because the whole DRAM rank or a bank is unavailable while the refresh operation is going on. And it can also introduce long pauses to timings, and it can have some effect on quality of service or predictability. And yeah, so basically refresh rate also limits DRAM capacity scaling because as you increase your capacity, as you increase the number of rows in your DRAM chip, now you need to refresh more rows periodically. And at some point, you actually cannot fit all those refresh operations in the time window that you have. Okay, let's begin with some analysis. So imagine a system with 8 exabyte DRAM. So it's like a lot of bytes, and assume that a row is like around 8 kilobytes, which is quite realistic for the modern DRAM chips. There are a lot of rows here, right? So I'll not go through the math. I just show the questions. So just think about it. Like you have many rows. You need to perform all these refresh operations in a 64 millisecond time window. Now maybe like even 16 millisecond time window. And you will need to consume a lot of power, a lot of energy for doing that, and it's really bad if you think about it. So this is an analogy of a leaky DRAM cell. Basically, it leaks, and yeah. So let's look at the refresh overhead in terms of performance or different DRAM device capacities or densities. As you go from like 2 gigabit to 64 gigabit going to feature, basically, well, it's not so much feature anymore, but you can see that the time spent for refresh operations is quite a lot. It increases significantly. And similarly, energy consumption also increases. And we care about performance and energy, so we need to tackle this DRAM refresh problem. So how can we solve this problem? I'll start with the first observation that all DRAM rows are refreshed in every 64 millisecond. Again, you can change the number to 60 millisecond to adapt to today. And critical thinking question is that do we need to refresh all rows every 64 millisecond? As we saw in latency related works, there's a huge heterogeneity across DRAM cells. So maybe there is some heterogeneity here as well. So what if we knew what happened underneath in DRAM cells and expose that information to upper layers? Can we make use of this heterogeneity? So underneath, this is what happens. So this box represents all your cells in the DRAM chip, and let's say all rows. And when you look at the characteristics of these rows, actually only a small fraction requires refresh operations every 64 or 128 milliseconds. And there's this small fraction here, the yellow one, is in this range. And then for the vast majority of the rows, you can even apply some refresh periods of like larger than 256 milliseconds. So why do we have such heterogeneity? Because manufacturing is not perfect, and not all DRAM cells are exactly the same. Some of them are stronger than the others. Some of them are more leaky than the others. And this is called the manufacturing process variation. So how can we take advantage of this profile? Assume we know the retention time of each row exactly. We measured every single one of them. And can we leverage this information? Yes, we can. So it's a short answer. So how can we do that? So who needs to deal with that? And how much information do we need to expose? And this is important because like the more information you expose from DRAM chip to the other layers and stack, you need more complexity in that communication. It affects the hardware, software, overhead, power consumption, verification, complexity, and cost. And how do we determine the profile information? So these are all questions when you try to implement something to basically leverage this heterogeneity. Also, who determines it? So just think about all layers of the stack, right? So we are observing something in the device level, and then we need to basically touch the design of other layers here. Okay, so the first work, okay. So first we start with the testing the real DRAM chips using these new real experimental infrastructures. These are earlier versions of SoftMC, so I guess you don't have to worry about these, but you can just use SoftMC or DRAM Bender. So this is another picture of the setup where we have like multiple DRAM chips in different heat chambers, and we are simultaneously testing many rows over there, many chips over there. We have a temperature controller. We set the temperature in these heat chambers. We have FPGAs that send DRAM commands to these DRAM chips, and we measure their data retention time. So this is developed for DDR3 DRAM chips using the Xilinx board, and we control temperature. We test 248 commodity DRAM chips in this work, and it covers like 7 families based on equal capacity per device. And this is what we observe as you increase refresh interval. So going from left to right, you refresh less frequently. At 64 milliseconds, there's a cutoff, so you don't observe any bit flips until then. And then from 64 milliseconds to 128, you only observe bit flips like around 30 in like 30 DRAM cells, right? And if you go to 256, then it's like about 1,000 cells, and it increases like this. So if you think about the whole DRAM capacity, these numbers are quite small. So can we exploit this to reduce refresh operations at low cost? That's the question. Yeah, only 1,000 rows out of like 32 gigabytes of DRAM chip experience bit flips here. So our key idea is refreshing weak rows more frequently and all other rows less frequently. And it goes to the design of this mechanism called Radar. Yeah, so this is the paper that's published in ISCA 12. Okay, so the first step of Radar is the profiling. So you need to identify the retention time of all DRAM rows, and it can be done in the design time or during the operation. And the second part is binning. So you need to maintain this information somehow in an efficient way. And you need to store rows into different bins so that you can refresh each bin at different refresh rates. And we use balloon filters for efficient and scalable storage. I'll explain it in more detail. So this is the profile that we observe from real DRAM chips, that only a small fraction of the DRAM rows that require frequent refresh operations. Okay. So this is like, I'm just jumping to the end to show that it requires like very little storage in the memory controller to identify the retention behavior of different DRAM rows for a 32 gigabyte DRAM memory. And the third step is refreshing. Basically, memory controller refreshes rows based on their need of refresh rate. Okay, so here we have the system that has 32 gigabyte DRAM module, and it simulates an 8-core system for various workloads. And the hardware cost is very little. And we can reduce the refresh operations by 74% just by adding this like 1.25 kilobytes of metadata. And it translates to a significant reduction in the DRAM energy consumption, around 16%. And it also reduces the idle DRAM power consumption. So it's about 20%. It provides some significant performance improvement. And when you scale DRAM density, this is the more important part actually, because we don't care about how much gain we get at 4 gigabits of DRAM module, right? So 4 gigabits of density. We need to project for future DRAM chips. We know that density is increasing, and by increased density, actually, the benefits of Radar increases quite a lot. So this is the full reference for Radar. And there are more supplementary papers that help you understand the concept if you're interested. So here we have the first takeaway, breaking the abstraction layers between components and transformation hierarchy levels. And knowing what is underneath enables you to understand and solve the problems. And we need cooperation for that, right? So cooperation between multiple components and layers can enable more effective solutions and systems. Until now, is there any question? If not, I'll dig into more details. Yes. 72. Very specific. I'm not sure. This one? No?
Given that software cells are in the left side, would it make sense to just do profiling and identify all these cells and avoid using them altogether instead of...
So you can just retire them, you can sacrifice your DRAM capacity. That's another way of doing that, yes. But it goes a bit against the idea of like increasing your density, right? Because you want to have more capacity in your DRAM. If you fill up all your capacity, then you will need to go to SSD, right? It requires more latency. So we want to keep the capacity if possible in this work.
That's another way of exploiting the variation. So
that's true.
I think it makes sense if the trade-off makes sense. And then once you retire those cells, you're back to a similar picture after that. And then you can, you see what I mean? You're basically climbing that curve, that exponential curve that you showed earlier. But yes, that's another way of exploiting. It creates some issues. Basically, your physical memory space is not contiguous anymore. So you'll need to know in your operating system that which parts of your physical memory space are actually not allocatable, let's say. So it complicates the system software a little bit. This is completely transparent to the system software. It doesn't require any changes to software. But once you start deallocating or not using part of your physical memory, your firmware or the system software needs to be aware of that.
Okay, I will go to details then. So this is a nice quote, like good ideas are a dime a dozen. Making them work is oftentimes a real contribution. Yeah, I think it's really important to make use of this finding here. Okay, so the first part is profiling. So to profile row, we basically follow a really simple testing method. So we write some data to the row. We prevent it from being refreshed for some time. So we wait without doing any refresh. And then we read back the data. We measure if there's any bit fill-up. So we try it with different time windows, and we understand like how much time this row can retain the data. So we call this DRAM retention time profiling. Is it not that easy because it requires a lot of iterations with the different data patterns and temperatures, and there are some other phenomena playing roles in. Yeah, actually, it came in the slide. So the two challenges of retention time profiling are the pattern dependence and the variable retention time. So I will go through them quickly. So the first challenge, the pattern dependence. So retention time of the DRAM cell depends on what kind of data you put inside the DRAM cell. Basically, you can put a high voltage or low voltage, or it can be charged or discharged, right? So depending on the state, it can its data retention time changes. So when you activate a row, basically all bit lines are perturbed simultaneously. So you activate all the DRAM cells in a DRAM row simultaneously. And you can have different data stored in different bits or different cells. So that complicates the things quite a lot. And also there is some effect of the neighboring cell's data pattern on a particular DRAM cell as well. Okay. So yeah, there's electrical noise on the bit line affects the reliable sense of DRAM cell. So we will actually see this more effect of this in the RowHammer part of the lecture as well. But for data retention as well, this noise on the bit line affects or word line affects the reliable sensing of the DRAM cell, and the magnitude of this noise is affected by the for the bit line. The magnitude is affected by the data you store in the neighboring cells. So yeah, in this case, it's called bit-line coupling. In RowHammer, we will see word-line coupling. So you have some data in this blue bit line and some other data in the red bit line, then they can change the reliability of that sensing process. There's also a bit-line word-line coupling. Basically, you activate this word line with some relatively higher voltage to enable these access transistors, and that can also introduce some noise on the sensing. Okay, so the retention time of cell depends on the data pattern stored in the DRAM cell itself, also in the neighboring cells. So you basically need to find the worst case for the data pattern to understand the worst data retention time while testing. So that's one challenge. And so any retention time profile mechanism must handle data pattern dependence of retention time. And an intuitive approach is to identify data pattern that induces the worst case retention time for a particular cell or device. But it's quite hard to know at the memory controller which bits are actually interfering with each other, because there's some basically the mapping is not very transparent, it's opaque. And so when you use a DRAM row address or column address, you don't exactly know actually which row, which column that address corresponds to in the physical area of the DRAM cell. It can be obfuscated. And also there's some remapping going on for the faulty bit lines to improve yield after the manufacturing. So some rows and columns are moved in the post-manufacturing testing phase. So it also complicates things a little bit more. And so also worst case coupling noise is affected by non-obvious second-order bit-line coupling effects. So there are many types of noises actually in this circuitry. The second challenge is variable retention time. This is quite a curious phenomenon actually. So retention time of a DRAM cell can change randomly over time. So a cell can alternate between multiple retention time states. For simplicity, we talk about two states usually. So the leakage current of a cell changes sporadically due to the charge trap in the gate oxide of the DRAM cell access transistor. And if the trap becomes occupied, then it causes some leakage inside the transistor that can reduce the data retention time. And this is called trap-as gate-induced drain leakage. And this process appears to be a random process based on the prior work. And the worst case retention time, unfortunately, depends on this random process. So basically, to find this worst case, you need to test the same chip over and over again, expect that this random process will happen, and then find the worst case. So this is an example of that. So this is a single cell's data retention time on the y-axis, and on the x-axis we have hours of testing, basically. So as you can see, like it can jump quite significantly across different states. So we basically need to find this minimum value, and for that we need to test this cell for like 6 hours. It's quite expensive. And if you look at the distribution of this like minimum retention time and maximum retention time for the fraction of DRAM cells, actually there is some like significant variation you can observe here. So only these cells in this diagonal alignment show the minimum and maximum retention time the same. So if you can maybe expect no VRT for these, but for the others, it's quite significant change. So, okay, most failing cells exhibit VRT. So it's something important. You cannot ignore it basically in your testing time. Okay. So, so there is no straightforward way basically to trigger this random process and, you know, force a VRT to happen, and then you can test the worst case. It's a memoryless random process. It randomly happens, and it complicates the retention time profiling for DRAM manufacturers, and it requires more exposure to. So if you expose the chip to high temperatures, it can induce VRT in cells that are not previously susceptible. So it even makes things worse, right? So maybe you identify precisely which cells are susceptible to VRT, and it can change over time. And it can happen during soldering DRAM chips. It can change over time. The retention time profile may not be accurate. And one option of this one option for future work is to use ECC to continuously provide DRAM while it's working to aggressively reduce the refresh rate. And we need to keep ECC overhead in check, of course, for that. And this paper actually investigates this quite rigorously. And next paper I will talk about. I'm a bit sorry. Okay.
Okay. Are there questions on this one?
Okay, how can we find DRAM retention failures if in presence of these two challenges, basically? So how can we reliably find them? We want to have this so that we can make DRAM reliable and secure and make techniques like RAIDER work, save performance, save energy, and we want to improve them. And there are actually several papers that talk about all these. So this is one of them, but I'll talk about Avatar because it's particularly tackling the variable retention time. So the insight is that we can avoid retention failures if we use ECC, if we upgrade RAW on ECC error. So here we have maybe in the next slide it will be easier. No, okay. So our observation is that we have a rate of VRT that is larger than the soft errors. So if we use ECC, it keeps correcting errors as they happen. And then if we observe a new error, then we can say that this can be because of the VRT. And ECC corrects this, of course, but we can change the state of this particular row based on this corrected error. And we can start refreshing this row more frequently than before. So this is basically the key idea here. So you protect the row from the future retention failures. So basically, Avatar mitigates VRT by increasing the refresh rate when an error happens and ECC corrects it. And it requires scrubbing the rows around like every 15 minutes, which is a quite large time window, if you compare it to the refresh windows. And by doing that, Avatar can reduce the number of refresh operations quite significantly. And it requires testing once a year to increase refresh reduction from 60% to 70%. When you look at the speed up benefits of Avatar for different DRAM die densities, you see some significant benefits, of course. And as your DRAM chip gets denser, your benefits increase quite a lot. And there's also significant reduction in energy delay products. This is important if you're also worried about energy, which you should be. And yeah, this is the full reference for Avatar. You can read it. there are also more works that I will not go into details, but I will just show here about the data dependency. So Parbor is one of them. This other work from Samir Khan is also tackling that. There are quite a lot of works actually that tackles this data pattern dependency and the variable retention time. But I want to focus on this particular work called Reaper from Minesh. It's also from our group. This basically handles both DPD, data pattern dependence, and variable retention time in the data retention profiling. So it starts with the observation that only a few cells require frequent refreshing, as Raider showed before, because in a DRAM chip you have strong and weak cells. So weak cells leak fast, some strong cells leak slow. So and it's hard to identify which cells are those under different process variations, voltage, temperature, variable retention time, data pattern dependence. So our goal here in this work is to quickly and efficiently identify these error-prone cells. So we study the data retention characteristics of 368 chips here, and we identify cells that are more likely to fail at an increased refresh interval or temperature. And we also profile, in the second step, we profile our profiling also involves a complex trade-off space in speed, coverage, and false positives. So the key idea of this reach profiling or Reaper method is that you operate at a low refresh interval, so high refresh rate, and low temperature. And from time to time, you want to repeat your profiling for a DRAM chip. So you move to another operating condition. So you reduce the increase the refresh interval, reduce refresh rate, and increase temperature. So you exacerbate data retention. Reduce data retention time. So by doing this, you can perform the profiling faster. It's more reliable, and of course, you can have some false positives. This method basically improves the profiling time significantly, and it enables operating at longer refresh intervals by reducing the overall profiling overhead. So it provides performance improvement, end-to-end performance improvement around 16% and around 36% DRAM power reduction by tackling this refresh overheads. Okay. Are there any questions? Okay.
Maybe I'll make a comment. I mean, all of these works show that even though an underlying phenomenon is kind of obvious and it seems easy to exploit, I think it's very hard to exploit, really. You need to take into account all of these effects. So our initial paper, like Raider, I think it's a beautiful idea, but it just doesn't work the way it's proposed, right? That's why we really built this infrastructure to understand whether we can make that idea work. And we explored a lot of that infrastructure, enabled us to do a lot of things, including RowHammer that we will discuss. But I think these works on retention are extremely important, and they're going to become more important into the future. Like this variable retention time phenomenon is fascinating. In the end, it's a quantum-like effect that happens in the circuit that changes the retention time randomly. And it basically destroys your profile almost immediately, right? Because the profile that you had for a cell, you tested the cell for 24 hours, if you're lucky, and you figured out the retention time is 1 second. But then if you had tested it 25 hours, you would have figured out that the retention time is actually dropped to 8 milliseconds, right? So how do you find that out, right? That's why we have moved to a lot of online profiling mechanisms. But online profiling is not easy if you don't have error correcting codes, because you need to understand what you're dealing with, right? You reduce the refresh rate, you figure out if you've done the right thing or not. So that's why you need to have error correcting codes. So the system becomes more complicated to really exploit this underlying phenomenon that you have a lot of heterogeneity in retention times. And in the end, where does that complexity go? Into the memory controller. So if you have a very intelligent memory controller that can do this online profiling. The Reaper paper, for example, if you could go back to that slide, the Avatar and Reaper papers actually built on top of each other. Reaper is the build on top of Avatar. And these actually exploit the error correcting codes to do the profiling dynamically while the system is running. So it's very interesting because you actually plug in some DRAM and you may start with refresh rates that are high. And over time, you figure out which cells you can refresh less frequently. And over time, your performance improves and energy efficiency improves. Sometimes you make mistakes, meaning you should have refreshed some cells actually not so less frequently, but you figure out those mistakes during profiling and you adapt over time. So I think this is kind of a vision for a system that is much more adaptive as opposed to, and this also enables other things, right? Manufacturers are having a very difficult time to determine what's the refresh rate, for example. Maybe they don't need to deal with that as much. Maybe they actually say, okay, this is my refresh rate. It's very high. You start with that, and over time, your system becomes better. Does that make sense? So I think these works are really important because that they have a different mindset. And in the end, it requires intelligence in the memory controllers. Yes?
Does it mean that we need more memory, like reliable memory with the DRAM, where we can store the characteristics or
Yeah, that's a good question. Basically, where do you store these characteristics, right? This profile. I mean, in our work, basically, we store it in the memory controller, so it's reliable. It's an SRAM in the memory controller, but that requires you to profile every time. But if you envision it to actually to reuse the profiles across runs, then you need to store it somewhere probably in storage and then bring it back. MVM, yes, exactly. Any other questions?
Maybe I can make a quick comment
Go ahead.
about that as well. So in these works, we don't see that, but if you look at the recent literature about RowHammer mitigations, the latest update in DDR5 that Nisa will mention actually suggests that you keep how many times you activate a row, like that's a metadata, right? You keep that activation count inside the DRAM array, which is also actually susceptible to RowHammer. But you also protect that, something like that. So you need to ensure that reliability. But I think there are multiple ways of storing that metadata. Okay. So the next set of papers actually tackles this problem from a different aspect. So as we move to newer generations of DRAM chips, we started seeing that DRAM chips already internally implement some error correcting capabilities. And this actually obfuscates the bit errors as they happen in the circuit level. And it makes our lives a bit harder for profiling these. So these works tackle that. So the first one is Ein, the other one is Beer, and the last one is Harp. So these three works altogether actually addresses how can we handle while there is on by ECC inside DRAM chips. So this is a cartoonish summary of that. So you have some unreliable memory. Within you have some arrays that you can store your data, and then there's some on-die error correcting capability code over there. And on the left you have profiling, right? So you want to understand which bits are at risk of error, but on the ECC changes how errors appear to the profiler. So you sometimes a bit flip happens in the data storage, but you do not see that because that bit flip is corrected by ECC. Sometimes there are a lot of bit flips that ECC cannot correct, but it gives you a different distribution of those bit flips trying to correct those code words. So our goal here is to understand and address any challenges that Onda ECC introduces for error profiling. So these are the challenges. The first one is exponentially increasing the total number of at-risk bits. The second one is making it harder to identify individual at-risk bits. And the third one is interfering with commonly used data patterns for memory testing. So in this concept, we basically have two sources of errors. The first one is the direct errors as they appear inside the DRAM circuitry. You can observe them. And the other one is indirect error. It's a bit flip that is induced as an artifact of the error correction algorithm. So yeah, these errors are upper bound by the ECC algorithm. It depends on what kind of algorithm you put there. And the key idea is to decouple the profiling for direct and indirect errors here. And how we do it is the first step is the first one is active profiling. So it quickly identifies all direct errors with existing profiling techniques using on the ECC bypass path. So you basically bypass the ECC and then observe the bit flips as they appear. And in a reactive profiling, you also identify the indirect errors. Basically, you read it after the ECC correction happens. And by doing that, you can decouple these, and you reduce the problem of profiling with on the ECC to profiling without on the ECC. So you can, by following this methodology, you can observe bit flips as they appear in the circuitry, or you can, reconstruct the original bit error distribution inside the DRAM chip. So HARP improves the coverage and performance relative to the two state-of-the-art baseline profiling algorithms that tackle a similar problem. And HARP outperforms the best performing baseline in a case study of mitigating data retention errors. So HARP overcomes all those three profiling challenges to enable us profile this, get the data retention profile of the chips that are implemented on the ECC as well. So this is the full reference of HARP. It has artifacts evaluated, and there are a lot of versions of different talks in different lengths, so you can check them if you're interested. Are there any questions here? If not, I'll go back to Radar. Because we kept talking about the first step of Radar, about profiling, but there's another step that is binning. So basically we need to assume that we have the profile. We need to store rows into bins by retention time. And we should do that efficiently so that we do not consume a lot of hardware cost. Here we use a very old algorithm or data structure called Bloom filters. Are there anyone familiar with Bloom filters? Okay, a bunch of people. I'll just cover it quickly. So it's a way of understanding efficiently if an element is in a set or not. So as it's okay, I'll just go through the slides. So it's a probabilistic data structure that compactly represents the set membership information. And so if you want to do it in a non-approximative way, then you need to use a bit for each element to identify if that element belongs to a set or not, right? So you do some approximation here. You use some hash functions to share some bits, and you use a much smaller number of bits to indicate an element's presence in a set. So some elements map to bits that other elements also map to. So there is that aliasing. And you have three operations here called insert, test, and remove. So yeah, here's a more pictorial, easier to understand representation of that. So it's basically, you have a bit array over there, and you have multiple hash functions, and you want to insert a row ID to this set of that corresponds to the bin of rows that needs to be refreshed every 64 or 128 milliseconds. So basically, when you provide this row address to three different hash functions, they generate some addresses that are pointing to this bit array in different locations. So you go and set those bits from 0 to 1. And once you want to test, or you're curious if row 1 belongs to this particular set, if row 1 needs to be refreshed every 64 milliseconds, you provide the row address to these hash functions again, and they generate the same addresses. And then you go check all the addresses. If all of them are set, then you conclude that this row belongs to this set. If some of them are set, some of them are not, like when you add all these, the result is 0, right? So the first hash function points to a place where there's a bit 0, even though hash function 2 has like bit 1 or logic 1 as a result. You do not have logic 1 as a result in all of the hash functions. So you say the conclusion is that this row does not belong to this set, so it does not need to be refreshed every 64 or 128 milliseconds. So you can insert another row, and it will set a different set of bits. And it can happen that you test a row 5 here, and then these hash functions generate those pointers in a way that they all map to the locations where logic 1 is stored. So even though row 5 was not inserted into the set before, so it's because of the aliasing, you know, like different rows can map to the same bit. And as a result, you can have a false positive. So in this context, false positive means that row 5 does not need to be refreshed every 64 milliseconds, but you get the conclusion that it needs to be refreshed every 64 milliseconds. Yeah, this is the paper that proposes balloon filters. This method enables us to store the metadata in an efficient way, and inserting and testing for set membership is quite fast because you only go through some hash functions and check some bits, and you just perform an AND operation, which is quite fast. And there are no false negatives. There's no possibility of that you ask for a row if the row needs to be refreshed every 64 milliseconds, and the row actually needs to be refreshed in 64 milliseconds, and you get the answer of no. So there's no possibility of this, but the opposite is possible. So it enables trade-offs between time, storage efficiency, false positive rate. You can increase the size of this balloon filter, so it increases the accuracy. You store more metadata, but you get more precise, more accurate results. The disadvantage is that it gives you false positives. Basically, you can refresh some rows more frequently than they actually need. So this doesn't cause any harm for reliability concerns, but it can give you some extra performance overheads. Okay. So, yeah, a row may be declared present in the balloon filter, even if it was never inserted. It's not a problem. I already thought about it. So there are no false negatives. So you always refresh rows at least as much as they need to be refreshed. It's quite scalable because a balloon filter never overflows, unlike a fixed size table. So you can put more rows inside the same size without changing the size of the balloon filter. It just reduces your accuracy. It can give you more false positives. It's quite efficient. In this work, for a 32 gigabyte DRAM chips rows, we only need 1.25 kilobytes of metadata stored in these balloon filters. It's useful when you can tolerate false positives in set membership tests, and it's used in all these 3 papers actually so far from our group. There are many uses of these balloon filters as well. We are in love with this data structure. It's quite useful. Okay, so let's go back to Radar. The third step of Radar, refreshing. So you choose a refresh candidate row, and then you determine which bin the row is in. So you basically test the balloon filter structure over there. And then if the refresh is needed, you perform the refresh, and if it is not needed, you skip it. In this in this paper, we have two Bloom filters. The first one checks if a row needs to be refreshed every 64 milliseconds. If not, it's like a decision tree. So the second Bloom filter checks if it needs to be refreshed every 128 milliseconds. And if the answer is false, then the row is refreshed every 256 milliseconds. So this is like quite fast of a decision-making process. So you can implement this radar in two different ways, basically. So this is our baseline design. There's a memory controller, there's a DRAM chip. Inside the DRAM chip, we have the storage, banks, and the control logic. So refresh control is in DRAM in today's auto refresh system. So basically, every 7.8 or 3.9 microseconds, memory controller sends a refresh command. So if you want to be compatible with that, you can implement radar inside the memory controller. So it's very small data structure, 1.2 kilobytes. And it's almost nothing, basically, in the memory controller. An alternative is that you can also implement this metadata inside the control logic inside the DRAM chip. And it gives you like extra 20 bytes of Bloom filters for a 4 gigabit chip. So I already went through these results. I'm not going to reiterate them. So here's the question. What else can you do to reduce the impact of refresh? So I guess I can just stop here and ask for like if there's any opinions. If not, I can continue. Okay, so these are actually more questions for food for thought, right? So what else can you do if you know the retention times of rows? What can you currently measure the retention time of DRAM rows? So there are some discussions in this paper. It's a nice paper that shows all the implications of retention time profile mechanisms and a good experimental study. So you can find more information over there. So the last piece of the data retention part, I'm gonna cover another paper that is a bit more recent. It was published in Micro 2022. So here, what we do is we leverage the subarray level parallelism on off-the-shelf DRAM chips. So we start with the key insight that if you concurrently activate two rows, this row A and row B, and assume that these rows are stored in two different subarrays, you can end up refreshing one row while concurrently accessing the other row. And this is what happens in off-the-shelf DRAM chips when you violate the timing parameters quite aggressively. So this operation, we call this operation HERA, and we test 56 off-the-shelf DRAM chips from SK Hynix and show that HERA reliably works on those. And it gives us, it reduces the time spent for refresh operations about half, basically. So to leverage this, we also propose a mechanism that generates periodic and Nisa will talk about those later, RowHammer preventive refreshes with a deadline. And it buffers these refresh requests in a queue until their deadline comes. And it finds the opportunities of performing these refresh operations with other accesses in parallel by leveraging the subarray level parallelism. We evaluate HERA and show that it can significantly increase system performance by reducing the time spent for RowHammer preventive refreshes and periodic refresh operations. And we can also implement it at low cost. This is pretty much the end of DRAM refresh session. So it's a quick summary. DRAM refresh is critical challenge. It becomes more critical when we scale DRAM technology. We already discussed like several promising solution directions. There are many more in the field. And we examined the properties of retention time behavior. We talked about VRT. And there are many other avenues for overcoming different DRAM refresh challenges. You can still find handling data pattern dependence and VRT and active research problem. And enable online retention time, profiling, and error mitigation is also important going forward. Exploiting application behavior is also important, of course. Okay, so there are more papers that I will just show here. And you have the slides, you have all the links. If you're interested, you can take a look at them. I'll also remind you about this industry paper that Onur mentioned yesterday that calls for intelligent memory controllers. And with this, I'm done with DRAM refresh. So next we have a few slides about RowHammer, but we can stop here and get some questions. So we are already over time. Should we continue with RowHammer, or?
I think we discussed RowHammer yesterday, so maybe it's time to part. I think Ha-Sung will cover RowHammer later on, right?
Yes.
Any questions on refresh, latency? Otherwise, lunch. Lunch sounds good.
Okay, thank you very much for attending now.
Good afternoon.